today it's our pleasure to host Sylvia Biscoveanu. She's a PhD student in the group of Salvatore Vitale at the MIT, and I pronounce it very well, and working on gravitational wave data analysis, and with a particular interest in its applications of Bayesian statistics to combat binary parameter estimation and stochastic backgrounds. And she graduated from Penn State with a degree in physics and Spanish in 2016. So we're all looking forward to it. Take it away.
Thank you, and I will share my screen. Right, so can you see my slides?
Yes.
Okay, great. Yes, thank you for that kind introduction. So today I'm speaking on behalf of some of my collaborators, Max Isi, Salvatore Vitale, and Vijay Varma, and I'll be telling you about how we can use gravitational wave observations of binary black holes to measure their spins. So the compact binary systems that have been detected by LIGO so far in gravitational waves are characterized by 15 parameters. The intrinsic parameters are the masses and the spins. So the spins represent 6 of the 15 parameters. For each of the objects in the binary, you have one 3-dimensional spin vector. Its magnitude, which you can see here, is represented by chi, and then the tilt with respect to the orbital angular momentum is given by theta. And then there are also 2 azimuthal angles that determine the relative positions of the 2 spins of the 2 objects. So I wanted to start by asking you to reflect on your perception of the spins of the black holes that have been detected by LIGO and Virgo so far. For me, there are 2 things that stand out. One is that they're difficult to measure, at least compared to the constraints that are obtained for the component masses. And the second thing is that for most of the systems observed so far, their spins seem to be either very small or consistent with no spin at all. And this puts some interesting tension with the spin measurements from black holes in X-ray binaries, which in many cases have high spins or are even consistent with being maximally spinning. And so this chi parameter, the spin magnitude, is dimensionless, and it ranges from 0 for non-spinning systems all the way up to 1 for a maximally spinning black hole at the Kerr limit. And those 6-dimensional spins are quite hard to measure, and instead, when we're talking about spin measurements from gravitational waves, we tend to talk about 2 effective spin parameters. The first is chi effective, which is the best measured spin parameter with gravitational waves, and it is the mass-weighted spin aligned with the orbital angular momentum. So if you take each of your individual object spin vectors and project them onto the orbital angular momentum, you end up with this factor of cos theta, and then you multiply by some factors of the mass ratio. And this is kind of a strange definition, but one way to think about it is that chi effective is to spin as Chert mass is to mass. So these 2 parameters in particular are very well measured because they enter the waveform at a lower post-Newtonian order, so they have a bigger effect. And then for systems that have spins that are not perfectly aligned to the orbital angular momentum, this introduces an effect called precession. So it causes the orbital plane to wobble, and the inclination angle between the observer and the system changes. And so this results in an amplitude modulation of the observed waveform. And so one parameter that is used to encapsulate this effect is called chi-p. This is the effective precessing spin parameter, and this is the mass weighted spin projection, this time onto the orbital plane. So you have these factors of sine theta, and again, some factors of the mass. And this was mostly introduced by the waveform modelers as a convenient way to ascribe this effect of precession onto one parameter. And now just to take a step back and talk about why we even care about measuring spins. In this case, it's because spins carry important signatures of the compact binary formation channel. So there are typically two most popular formation channels that are considered for the Barney black holes that are observed by LIGO and Virgo. The first is field formation. So in this case, two stars that are born together will evolve together. So they'll start undergoing an episode of mass transfer from the more massive to the least massive, and then the more massive star will go supernova and eventually collapse to a black hole. And at this stage, you're left with something like an X-ray binary system where the remaining star is accreting onto the black hole. Eventually, the secondary star will also go supernova, leaving a black hole, and if they're close enough, they will merge, and we can see this emission in gravitational waves. And in this scenario, because the stars are born and evolve together, they tend to have their spins preferentially aligned. The other common formation scenario that's discussed is dynamical formation. So this will happen commonly in dense environments like globular clusters. So in this case, the merging black hole system is assembled somewhat haphazardly through a series of interactions with other black holes or stars in the cluster. And because of this random formation, the spins of the final black holes that end up in this binary that will merge and be observed by LIGO will be isotropically distributed. So we can use these formation channels to interpret the spins of both individual events and the whole population of observed events. So, for example, if we find that all the events in the population have mostly aligned spins, that would be an indication that the field formation scenario is the dominant channel. Whereas if we find one system that has a particularly large in-plane spin, that might be an indication that it formed dynamically. And so you can use the full 6-dimensional spins for this sort of population analysis, but you can also use chi-p and chi-effective at some loss of information because you're taking 6 dimensions and projecting them down into 2. So for example, if you find that the chi-effective of your population is small, you won't be able to tell if that's because the spin magnitudes are small or because the tilts are large. And you can break some of the degeneracy here by looking at chi-p, but chi-p doesn't include any information about those azimuthal spin angles, which also carry interesting information about things like spin-orbit coupling or the efficiency of tides in the evolution of the system. So previous work has also looked at how well the spins of black holes can be measured using gravitational wave observations. So here I'm showing some results from a paper by Vitali et al. In 2016. And on the y-axis, they're showing the width of the 90% confidence interval, or the uncertainty in the measurement, as a function of the detector frame total mass of the system on the x-axis. And so the chi-effective results are on the left and chi-p are on the right. And these light shaded points are the uncertainties for the primary dimensionless spin magnitude. So there are a few things to point out here. First is that particularly for systems that have some in-plane spin component, the chi-effective parameter is much better measured than the spin magnitude parameter, as is expected. And then for both chi-effective and chi-p, you can see this nearly monotonic increase in the width of the 90% confidence interval as a function of the total mass of the system. And this happens because these extremely massive systems will merge at very low frequencies. So if the sensitive band of LIGO starts at around 10 or 20 hertz, these systems are also merging in the range of tens of hertz. And so you have very limited information about the in-spiral part of the waveform, which is where most of the information of the spins is imprinted. So as you increase the total mass of the system, you lose the ability to measure spins. And so we can look at one interesting case study of a heavy binary black hole system where the spins are seemingly well measured. And this is GW190521. This is a relatively new event from the latest observing run of LIGO, and it is the heaviest binary black hole system observed so far, and it has a possible indication of a dynamical formation channel. So here are some of the posterior probability distributions from the detection paper for this event. So you can see that the heaviest black hole in the binary has a mass of about 80 solar masses, and its companion is around 60 solar masses. However, when you go into the detector frame, the total mass of the system is around 270, so comparable to the systems that we saw on the previous slide. And then if we look at the spins, you can see chi-p on the x-axis here, and this probability distribution peaks at high chi-p, so around 0.8, and it shows a significant deviation from the prior, which is shown in black, and this is the best guess for what the chi-p of the system would be in the absence of any of the information contained in the data surrounding this event. So here, this is an indication that there is some high spin component in the orbital plane, whereas if you look at chi effective, it is consistent with peaking at 0, so the aligned spin component is small. And this begs the question, how can you actually measure chi-p so well for such a heavy system when we just saw that the spin measurements get worse when you increase the total mass of the system? And I can show you some very hot off the press preliminary results. So with my collaborators, we've been looking at updating these projections for how well you can measure spin for heavy binaries, folding in improvements in waveform modeling. So the previous results did not include the effect of higher order harmonics. If you take the waveform and decompose it into spherical harmonics, the dominant contribution will come from the L equals 2, M equals 2 mode, but the other modes are also important, particularly for signals that are dominated by the merger and ring down parts. And so in these updated results, we are using a numerical relativity surrogate waveform, which includes these higher order harmonics and is trained to numerical relativity simulations. And it also includes an improvement in the modeling of the spin evolution. So it models the full 6-dimensional spins, not just chi-p, whereas the previous waveforms computed the initial effects by moving into the co-processing frame, which is a line spin approximation, and then they would take those results and twist them up based on the chi-p of the system. So any information in the azimuthal spin degrees of freedom will be washed out. And so here with these new improvements in the waveform modeling, I'm again showing the width of the 90% confidence interval as a function of the total mass of the system. And you can see that there's some more scatter compared to the previous results, and that's one thing that we're still trying to see if this is a physical effect. But I'll draw your attention to one of the more prominent features. So here we're looking at systems with two different mass ratios. The blue are equal mass systems, while the red have a mass ratio of 4. And then the thickness of the line corresponds to the tilt of the primary spin. The secondary is non-spinning in this case. And then the solid lines are for systems observed nearly face-on, while the dotted lines are for systems observed nearly edge-on. And so one prominent feature you can see here is particularly in the blue equal mass systems for chi effective is that the width of the confidence interval seems to turn over, and there is a seeming improvement in the measurement of the spins at the highest masses that we've proved here. And this is one of the key differences from the previous results, which showed just a monotonic increase in the width of the 90% confidence interval as a function of the mass. So we're still trying to understand physically where this comes from. It's possible that we're gaining some information from the post-merger part of the signal at the expense of the in-spiral, or maybe the post-merger part of the signal is optimally aligned with the sweet spot of the PSD. But this is an interesting feature that could potentially explain why we were able to get such a good measurement of the spins for GW 190521. And again, these are quite preliminary results. And now I'll switch gears and talk about another degeneracy that makes measuring the spins difficult. So far, LIGO-Virgo analyses sort the components of a binary system into primary and secondary using their masses. So the most massive object gets the subscript 1, and its companion gets the subscript 2. And in this case, when you do the analysis, the priors will enforce that M1 must be greater than M2. And you end up in a difficult situation when you're trying to distinguish the two objects for systems that have equal masses, particularly when you're trying to measure their spins. So here we can see one such system that is affected by this degeneracy. It's a simulated system where the component masses are each 40 solar masses, and the spin magnitude of the primary is 0.8, and the spin happens to be entirely in the orbital plane. Then the secondary is non-spinning, and it has a moderately loud SNR of 30. And in this case, I'm showing again, the posterior probability distributions for the spin magnitudes and then the spin tilts. So in the magnitudes, you can see this circular or degeneracy where it knows that one of the two objects in the system is highly spinning, but because they're equal mass, it can't tell which. And so you end up with this hemispherical shape. And you can see a similar degeneracy in the results for the spin tilts as well. So here you can see it wants to constrain one of the spin tilts to be in the orbital plane, but it can't tell which because they have equal mass. So we instead wanted to ask, what if we sort the components of the binary by their spin instead of their mass? And in this case, the prior will be enforcing that the spin of the most highly spinning object is greater than the spin of the least spinning object. So we introduce 4 new parameters: the spin magnitudes and tilts of the most spinning object and the least spinning object. And in this case, we're labeling them as A and B, where A is the most spinning object and B is the least spinning object. So here I'm showing you again the posterior probability distributions for the same system, and this time with the spin sorting applied. So the spin sorting is in green here. And you can see that this has broken the degeneracy in the spin magnitude, so it's able to identify that the most spinning object has a spin of 0.8, while the least spinning object is consistent with non-spinning, as is the case. And it similarly breaks the degeneracy for the spin tilts. So the spin of the tilt of the most spinning object is constrained to peak around theta equals 90, whereas the posterior for the tilt of the least spinning object pretty much just returns the prior, as would be expected since the secondary object in this case has no spin. And this is just one example, but we found a similar improvement in the resolution of the component spin quantities for generic systems that were consistent with having equal masses. And this is a somewhat SNR-dependent statement, so you could have a really loud system that has a slightly unequal mass ratio, but if you're able to measure that it's unequal, then you won't necessarily get a similar improvement, whereas if you have a quieter system that might have a more unequal mass ratio, as long as the posterior is consistent with having equal masses, in this case, it might be beneficial to use this spin sorting. So we can also look at how this applies to some of the current LIGO detections. Here I'm showing 2 events, GW 151226 and GW 170729, that already had indications, even with the mass sorting, that they had some spin. So these are what are called spin disk plots. And how you read this is the magnitude increases outward radially, so more highly spinning systems will have more support at the outer edge, whereas the tilt increases downward from this 12 o'clock position. And so you can see here that already in the mass sorting, the posterior probability distribution has a broad support even for high spins for both of these systems. And then if we apply the spin sorting, you can see how the probability density shifts. So for both of the highest spinning objects in these systems, there's considerable support for them to be maximally spinning at the limit here, whereas the posterior support for the secondary shifts to lower values, and there isn't as big of an effect for the spin tilts in this case. So in this case, we're able to rule out that the primary is non-spinning at greater than 90% credibility, and we find considerable support for maximally spinning black holes at the Kerr limit for those two events. And we can look at one event that does have a measurably unequal mass ratio. So this is GW 190412, has a mass ratio of about 0.3. And so you can see here that actually the spin sorting is introducing some of the degeneracies that it was helping to resolve for the equal mass systems. In this case, the green posterior for the spin magnitudes, it knows that it wants to ascribe a spin of around 0.5 to 1 of the two components, but it doesn't know which, whereas in the mass sorting, it clearly is able to say that the spin of the more massive black hole is around 0.5. And you can see a similar degeneracy introduced in the tilts as well. So this is one example of a system where perhaps using the spin sorting doesn't help improve the resolution. So this is a really simple idea, and it doesn't add new information. It can be done entirely in post-processing after you've already run the initial analysis with the mass sorting. In this case, we're just changing the question from what is the spin of the most massive black hole to what is the spin of the most spinning black hole. And I just want to clarify that we are defining a new set of parameters. We're not just applying a new prior to existing parameters. So this means that there's no change in the Bayesian evidence, which determines how likely it is that the segment you're looking at in question has a signal or just has pure noise. And it also doesn't change inferences about the effective, aligned, or precessing spins. So the definitions of chi-effective and chi-p are in terms of the mass sorted components, and those don't change. And we can also try to determine the distributions of the spins across a population of detections, not just looking at individual events. And again, this new sorting doesn't change existing population inferences that use the mass sorted spins, with the possible exception of models that used only the marginalized one-dimensional posteriors that aren't able to encapsulate that degeneracy. And now we can instead calculate the population level distributions of these 4 new parameters that we've introduced and see how they compare to the mass sorted parametrization. So for the spin magnitudes, we model the mass sorted spin magnitudes as being drawn from the same beta distribution. So on the right here, you can see some examples of what a beta distribution looks like. It's characterized by 2 parameters, alpha and beta, and those are the hyperparameters that we are trying to infer in this population analysis using a series of detections. And we can distinguish between 2 types of beta distributions. So a singular distribution means that it can peak at the edges, so at chi equals 0 or at chi equals 1. It's still normalized, it just happens to diverge at the edges. And the non-singular beta distributions have to peak somewhere in between the edges, so the probability has to go to 0 at the edges. And so the red, green, and blue examples here are singular distributions, while the orange and purple are non-singular distributions. So for our population analysis, first we looked at events from the first gravitational wave transient catalog, GWTC1, and that was 10 binary black hole systems. So here is what we get when we apply this beta distribution for the mass sorted spins. This is just reproducing the analysis done in the Astrophysical Implications paper for GWTC1. So in the dark blue line here, you can see the posterior predictive distribution for the non-singular beta distribution, which is just an average over the different beta distributions that we obtained. And the shaded areas show the 50% and the 90% confidence intervals. And you can see the same thing in orange, but for the singular beta distributions. And then the dashed lines show what you would get if you used prior samples, which are uninformative, instead of the informative posterior samples for the 10 events that are going into our population. And so you can see here that in the orange singular distribution peaks at 0 for the mass sorted spin magnitudes, while the non-singular distribution peaks away from 0 because it has to by definition, but it still has considerable posterior support at chi equals 0. And so now what we want to do is take this inferred distribution for the mass sorted spins and instead infer the distribution of the spin sorted spin magnitudes, assuming that they're the maximum and minimum of 2 draws from this distribution. So we apply order statistics to obtain the distributions of chi A and chi B, and this is what we get. So on the left here, you can see the distributions for P of chi A. And you can see that in both the singular and non-singular cases, the probability peaks away from 0, so it has this peak at around 0.3. This tells us that most of the highest spinning black holes in LIGO binaries actually have some non-zero spin. If we look at the distribution for chi B instead, you can see that in the singular case, it's peaking at 0, and in the non-singular case, it's railing towards 0. So in this case, the secondary object is consistent with having mostly 0 spin. We can also look at the tilts. So in this case, instead of using a beta distribution for our population model, we use a 2-component model that encapsulates the physics of the formation channels that I talked about earlier. So the first component is a preferentially aligned component that represents that field formation scenario, and the second component is an isotropically distributed component. And the hyperparameters that we are trying to infer here are these sigma parameters, and this controls the width of the spin tilt distribution for the aligned component. So it peaks at 0, but it has some characteristic width, and sigma equals 0 means that all the spins in the population are aligned. And here I'm showing the posterior probability distributions for the sigma parameters under both the mass sorting in blue and the spin sorting in green. And so you can see that when you apply the spin sorting, it seems like all the information shifts to the tilt of the most spinning black hole. In this case, this green distribution for sigma B is flat compared to some feature here in the mass sorted sigma 2 distribution, whereas the sigma A distribution peaks slightly more away from 0 compared to sigma 1. And one other thing that's worth pointing out here is if you look in this lower left-hand corner, this is where sigma 1 equals sigma 2 equals 0 lies. And so this part of the parameter space is ruled out at greater than 90% credibility using both the spin and the mass sortings. And this means that not all of the systems in the population have completely aligned spins. And this would be an indication of evidence for spin precession in the population. So the results that I've showed so far were just using the first gravitational wave transient catalog, GWTC1, but we can now also look at applying this to GWTC2 since LIGO has released results from their first half of their third observing run recently. We can go back and look at GW190521, that particularly heavy binary system. So in this case, the spin sorting does help break some degeneracy in the spin magnitude. You can see again in the blue here for the mass sorting, the posteriors for the spin magnitudes have support at high spins for both the primary and the secondary under the mass sorting, whereas when you apply the spin sorting, the support for high spins shifts just to the primary, and it's consistent with being maximally spinning, while the posterior support for the least spinning object is more broad. And it doesn't have as big an effect on the tilts, mostly because those were weakly constrained to begin with, so there's not a lot of information there. We can also look at the population level results. So these are results from the Astrophysical Implications paper accompanying the second GWTC2 catalog. So again, here, this is the result for that beta distribution applied to the mass sorted spins. And you can see that it actually has more support for low values of the spin. In this case, I'm just showing the non-singular beta distributions. So the support has shifted down to lower values. And as a bonus, there's definitive evidence for spin precession in the population. So in this case, they just use one sigma parameter for both tilts instead of one for each, but you can see that it clearly peaks away from zero and it's bounded on both sides. So a much stronger constraint using 44 events in this case in the full O3A results instead of just 10 events that we used for GWTC1. And we can also apply our spin sorting to the O3 results. And here you can see again the distributions for Chi-A, the high spinning object, and Chi-B. So this peak in the Chi-A distribution is more prominent at around 0.3. And it's a better constraint, so the uncertainty region is smaller, as is expected when you're adding many more events. And for Chi-B, consistent with what we saw for the mass-sorted spins, the probability density shifts down towards lower values of Chi-B, and it's more strongly peaked at Chi-B equals 0. So with that, I'll just put up my conclusions. I've hopefully shown that it's possible to measure the spins of even the most massive systems following updates in waveform modeling that were crucial. And for equal mass systems, sorting the binary components by spin instead of mass can improve the resolution of the individual object spin parameters. This new spin sorting doesn't add any information or change existing inferences for population analyses using the mass sorted events, but it could perhaps be explored in a theoretical context, particularly through population synthesis. And I can take any questions.
Thank you, Sylvia. Thank you. It was very, very interesting talk. So questions? Yes, Avi.
So one question about the spin is there a significant effect as to the volume that we are probing? In other words, does it make a change in the statistics as a result of us being able to see systems that have high spin more easily with LIGO?
I see. So you can take into the account the effect of the detectability of the spin when you model the population. In this case, I think for the O1 results, the GWTC1 results, this effect was not taken into account just because it's secondary compared to the bias that you get from the mass. But I think it's starting to be incorporated more now. I think some of the O3 population analyses did take it into account, but accounting for that bias is difficult, and so it's just something that's starting to be done now more for population analyses. But yeah, it could potentially affect the inference. But if anything, as you said, it's easier to detect systems with higher spin, so the fact that we're seeing lots of systems with low spin is indicative that perhaps that is a true feature of the population.
Thank you.
I think Salvatore wanted to add something.
Yeah, right. I hope I can be heard. So what Sylvia said is true. I just wanted to add maybe a number, if you're interested, and point you to a paper, since we have actually worked on this with another students a couple of years ago. So it turns out that if I understand that your question is really, are we missing some of the events preferentially according to their spins, because some spins are easier to detect, they emit more energy pretty much, right? And the answer is yes. It's not a big effect. You can find the numbers in this PRD paper if you want later. It's of the order of 10% or so at most, okay? And there is some dependence on the underlying spin population, right? Because you can imagine that if the spin distribution it's flat, then something happens. If the spin distribution is, say, a power law, something else happens because you're just forming fewer highly spinning black holes. So this will only become a problem, which is basically what Sylvia said, when you have enough detections that the inference you can make is at the 10% level, because at that point you really need to start accounting for this effect thoroughly. And that was clearly not the case in O2. It is more borderline the case in O3 and will certainly be the case in O4. So that's why, as Sylvia said, people are now working more seriously on implementing selection effects induced by the spins. And for those who don't think about spins every day, what's happening is that you can basically think about spins as magnetic dipoles. If they're aligned, basically the waveform spends more time in your band because it takes longer to spiral, and that's more SNR. It's more signal to noise ratio, so those are easier to detect. If the other way around, they're hardest to detect, pretty much. Anyhow, sorry, that was a longer answer that I thought I would give, but hopefully that helps.
Thank you, Salvatore. I just wanted also to use this opportunity to advertise for everyone your excellent review that appeared last night on the archive. It's titled "The First 5 Years of Gravitational Wave Astrophysics." So anyone that wants to get an overview of the subject of gravitational wave astrophysics is welcome to look at that. It's archive 2011.03563. And of course, all of us are waiting for the next 5 years to see what comes along.
Thank you, Avi. It's very kind of you. If I just can ask something, don't ask me, please, for citation. I have a couple of 100 and I'm already at 100. So I already received 2 emails this morning. I would love to. I can't.
Yeah. Well, it shows the success of the field, the fact that there are so many citations that in principle you should have mentioned.
So at this point, I have a curiosity. You said that LIGO is measuring preferentially some spins. So it's easier to measure lower spins, higher spins? I don't have a clear idea about this.
Yeah, so higher spin systems will have an effect on the waveform such that it's easier to measure, whereas if you keep all the mass parameters the same. So this introduces this slight selection bias.
Mm-hmm. But it's not huge.
No, it's small, especially compared to what you get for changing the mass.
Okay, thank you. We have a question from Mohammed.
So I have a question about this O3 catalog. When you look at the systems that have in-plane spin, there is a preferential bias that you will see those which are very asymmetric to actually have their posterior on chi-p to be different from their priors. I wanted to know if this is some selection bias, some parameter estimation bias, or is it some physics that we see more constrained estimate on chi-p, but for systems that have Q, like mass ratio less than like 0.3 or 0.2.
Yeah, so this is, I guess part of it comes from potentially gaining more from the high order modes. So high order modes will have a bigger effect for more asymmetric unequal mass systems. And then it's possible that that has additional information about the spins as well. This is also one thing that we're trying to understand in the preliminary results that I showed at the beginning. So exactly right, you can see in this case for chi-p, the red lines are below the blue lines, which are for equal mass. And this is one thing that we are trying to understand. It's also possible that it comes from an improved constraint on the inclination. So the inclination angle affects how much precession you can see. And so if you can constrain the inclination angle, then that will also affect how well you can measure chi-p. It just has to do with the degeneracies in the system, I think.
Thank you.
Do we have any additional questions? So if not, let's thank our speaker again. And we will see you next week.
Thank you for having me.
I thank you for hosting.